Predict whether each geometric series has a finite sum. So based on the two examples we've seen before, we have to sort of figure out, is there a way that we can tell if something's going to get closer and closer and closer to a number, sort of like what we did in our initial one, where I just kept adding numbers, and you see that it keeps getting closer and closer to 0.333 repeated. If we look at 1/3 plus 1/12 plus 1/48 plus 1 over 192, at this point, it's at 0.86. Oh, I forgot a 12. Second. Second, insert the 1. All right. It's at 0.442. If we added the next number, we would have to add 1 divided by, and we'd take 192 and multiply it by 4. Which is 1 over 768. And now we're at 0.444. Do you think if I keep adding numbers that this answer is going to get closer and closer to an actual value? And in that case, we would say the sequence or the series converges? Or do you think our answer will just keep getting bigger and bigger and bigger? And why? Do you think this one's getting closer and closer to a number? Like the 1/3 one? Yeah, it appears to be. One of the reasons is because what's happening each time here? In our first example, r is 1/4. The amount that we're multiplying each term by is 1/4. Eventually, what's happening to the numbers that we're adding? Like the next one was 1 over 768. How much did we add when we added 1 over 768? Not a lot, right? It's really, really close to 0. And if you multiplied it by 1/4 again, 768 times 4 is a really, really smaller number. I don't know, really, really smaller makes sense, but a much smaller number. And so these numbers we would say these numbers are getting closer to 0. And according to our calculations, it appears we were at 0.444. Maybe we would guess that this number gets closer to 0.444444. And it does. Does anybody know what 0.4 repeated is as a fraction? 4 over 9. For the second one, for part B, can you see in part B, r is equal to 2? You subtract 8, then subtract 16, then subtract 32, then subtract 64, then subtract 128. What do you notice about the numbers each time? This time, they're getting bigger and bigger and bigger. And if we added those numbers, our number is going to get bigger and bigger and bigger. Will it converge to a certain number? No. So whereas A had a finite sum, B does not. The values, as you keep on going, just get bigger and bigger and bigger. And so we can't say there's a number it gets closer to. In C, R value is negative 1 over 10. We're multiplying by negative 1/10 each time. So we subtract something, then add something, then subtract something, then add something. But the value that we're getting closer and that we keep doing here, same thing as this last one, these numbers are getting closer to 0. So does this one have a finite sum? It does. What's a pattern in the R values that's going to tell us whether something has a finite sum or an infinite sum when you add it up? Fraction. Okay, but I could write 2 as 4 over 2. Does that then make it a fraction that's less than 1? I guess it doesn't have to be a fraction because you could have like a decimal. But the key thing is okay, now I'm going to write it wrong to begin with. Okay, and you're going to have to see if you can fix. So we said a fraction, and then I came up with a fraction that didn't work. Then you said less than 1. I'm going to come up with an R value that's less than 1. How about negative 3? Will that have a finite sum? No. So we need the R value to be less than 1, yes. To be a fraction, yes. But how do we describe that? It's got to be between negative 1 and positive 1. So when negative 1 is less than R is less than 1, and sometimes you'll see textbooks put it in absolute values like that. When the R value is between negative 1 and 1, the infinite geometric series will have a finite sum. And this is where I believe, in this particular case, the math gets really quite beautiful. I know, laugh because you haven't described math as beautiful before maybe, but watch because this is really quite stunning. So we know our formula, right, for adding up geometric series. We learned that formula the other day. Our formula for a geometric series was Sn equals term 1 minus R to the n over 1 minus R. That's our formula on our formula sheet, right? Okay. When the R value is less than 1, okay, or the absolute value in R is between negative 1 and 1, I want you to think about what happens to this. So let's look at one of our examples. Let's look at, do you want to do the shaded box one? Let's put the answer for the shaded box. We started with 1/4, and then we added 1/16 and 1/48, 1/256, and here our R value was 1/4. Okay? If I wanted to add up the first 100 terms, that would be quite a few, my formula would say S100, term 1 is 1/4, 1 minus 1/4 to the 100, all over 1 minus 1/4. Right? And I want you to focus on how big is this number? Very little. Okay? And that's only adding up 100 of them. In fact, let's see if our calculator even still calculates that. If I do 1 divided by 4 to the power of 100, yes, my calculator says Move this decimal place 61 places to the left. So here we go, decimal 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 622305228. That is an extremely small number. If we added the first 1,000 terms, what's going to happen to this? Going to be even closer to a 0. In fact, on our calculator, if we keep adding zeros, eventually your calculator is going to run out of memory and just say, it's close enough to 0, let's stop. Okay? It couldn't do 1,000. Okay, let's see, could it have done 500? At what point is the calculator not able to do calculations? 500 it couldn't do. 250 you want to try?
499.
Oh my god.
250? Nope, can't do 250. Boy, this calculator is weak. How about 125? 125 it could do.
150.
150 you think it can do? 175? No?
150 for sure. It's only
You think 150 is the biggest number it can do? Oh, I mean, this is so fascinating right now. No, it can do 150.
You can do 155.
It can do 155. 158? Yes.
160.
160?
169.
160? 160 is fine.
64.
163.
164? 164 is fine.
165.
168.
160.
167.
Oh man, this is so intriguing. Oh, that's going to be that. Can it do 167?
Nope.
No.
65.
Stop 66.
Calm down. We'll get the answer soon. 164.
So 164 we did already, didn't we?
Yeah.
So 164 is the last one that worked. And then the calculator quit because it had so many zeros. What was 164? 99 zeros. That's as many zeros it could have. Right? Whew, I won't do that as a decimal because that'll just take too long.
164.5.
Ooh, now we're getting to 164.5. You can try. The last whole number was 164. But what is basically happening is we are going to make a formula. We're going to make a formula where we plug in infinity. Okay? Your calculator gave up at 164. 164, in the scheme of things, isn't that big of a number compared to 164 million. Or, so what happens to our formula? What happens to this thing when you put a huge number in there? It gets so close to 0 that we can ignore it. And if it gets that close to 0 that we can ignore it, what happens to our formula? This we can ignore. What's 1 minus 0? Right? 1 minus 0 will be 1. What's 1 times term 1? That's all that's left on the top. And on the bottom is still 1 minus r. This, in my opinion, is a beautiful formula. Okay? Because check this out. Let's look at this sequence that we did. We already know that the answer to adding these all up is 1/3. Check out the formula. You would put 1/4 in for term 1. 1 minus a quarter in the bottom is 3/4. How do you divide fractions? Multiply by the reciprocal. What's going to happen to your fours? They'll simplify, and you just get 1/3. Okay? Questions? 5, 6, 7, and 10?
I had to ask, didn't you? You got one.
5, 6, 7, and 10. Again, we're actually only going to do one more question. We are going to have our quiz.
I